Alors ici c'est le live. Ok. Ok, c'est l'air de fonctionner, on va voir si la musique passe maintenant. Bonsoir. Avec le son, je crois. J'arrive pas à transférer le son de mon Spotify sur... je crois que je n'ai plus de lancer. Oh, sorry, I was speaking French. Okay. I can't launch Caster for a reason that I don't understand. Just a minute. And I don't know why I can't do that. Anyway, let's do that without music then. Okay, welcome everybody to the new stream, part 3. I hope you will enjoy it. Just let me show your chat. If I see the chat here, it's welcome. Okay, I'm just going to open that here. Okay, good evening everybody. What you see in my background here is actually my new panel, not my new panel, but some animation on the panel, which I will show you does not require really any memory to drive. The trick here is actually to push, as we did earlier with the SPI, all the data at once, for once. Okay, so let's go back first to what we've done a couple of weeks ago. Okay. Great, let's start with that. So for you to remember what we've done last time, using SPI, we've displayed a nice strawberry for those ones, I guess. So I wrote phrase in French. So using the SPI, we were able to display one strawberry on one 16 by 16 panel. Okay, and that not using too much data, was what we use actually to push all the data at once it's been calculated. So that was easy part. Now, because here on what you see, you've got 12,000 different LEDs. What I'm going to do is actually show you the library that I've made, which I call icoclast driver with using shift registers, which allows me to control a lot of LEDs. We're going to start from scratch, and I'm going to start to display some stuff in here, and you will see how it works. Okay, so let's start from a brand new sketch. Sketch. Okay. Windows. Here it is. Okay. So we start with a brand new sketch. Okay. I'm going to define first the basic of what I'm going to do. So just going to declare what I need to declare for any other example of API. Let so I'm going to include my driver, which is square r less virtual driver.h. Okay, but before that, I need to tell him a couple of parameters to be able to do. So I'm going to tell him that I'm going to have this. This is how I drive with the PCB that I use to drive my panel. You've got here one shift, I would say 74 to 45, and here I've got shift register 595, and here I've used RG45 to send the data. And here you can put your nice ESP32. And here, as you see, I've got 6 of these HC595 shift registers. So I'm going to tell him, okay, I'm going to use 6 of them. And that I'm declaring that by saying serial pins. So I'm going to use 6. For each of my panels, I have 256 sleds. So I'm going to say that per strip or per pin, I've got 256 sleds. 256. I'm going to say that I use fast sled. This is only used to get the correspondency between my pixel object and the HSV of fast sled functionalities. Then that should be enough for the moment. I'm going to use to be able to use this shift register. Not only I need to tell him the pins that I'm going to use, but also a clock acknowledge pin. That's for the second. Now I'm going to have to tell him which pins I'm going to link my 72, my shift register to. Use. Okay, so the pins. And I'm going to tell him, okay, now you can initiate serial begin. I'm going to initiate my of course, I need a LED buffer. So what I'm going to do, I'm going to tell him that pixel LEDs num LEDs, and I'm going to define num LEDs as being number of serial pins multiplied by 8 because for each of my shift register I've got 8 pins, and times, and I do not forget to do this, encapsulate it in brackets, otherwise you can have issues. So, okay, that should be a trick. Here instead of over there. Where is my chat? Me, nobody for the moment. Okay, so I've got, I don't need 60 pin actually, I've got only 6 to be used. 1, 2, 3, 4. Why do I have 17? 1, 2, 3. Ooh, way too many. 2, 3, 4, 5, 6. These two are not used. And I just gonna press. Okay. Now I'm gonna initiate my panel. So the way to do that is pretty easy. I'm just gonna tell him, just initiate the LED with a pointer to my LED, the pins that I'm gonna use, the clock pin, the latch pin. Okay, pretty straightforward. Now I'm gonna do the simple loop for int panel equal 0, and I'm gonna cross to all my panels. 48, because I've got 48 panels of 256. What I'm gonna do now, I'm gonna create a small train of in each of the panel. For int for each of the panel, I'm gonna say, okay, for int e equals 0 point e strictly inferior at train size. I'm gonna define what it is later. 1 plus. So in my ladder array, to access one panel, I just need to tell him lets of panel times numlet plus strip, so that each time we put me on another panel, plus I need a start of the train start plus e, and I need to modulate that by numlet plus strip because it should not go further than one panel, and I'm going to put that equal Excel. Just going to do some right stuff. Okay. Now I need to define what is actually train start. That's equal 0, and my train size, I'm going to say that the size of the train is actually the number in the panel. The number of the panel. So it's panel because it starts with a 0. So it's going to be 1, 2, 3, 4, 5 until 49. Then I'm just going to display driver.show. I didn't define my driver yet. Oh. I have my driver, and I can call my driver and can say show. Okay, and I'm going to have a small delay of 100 milliseconds. Okay, let's me if I push that to a correct font, should be okay. So let's do this. So if I haven't made any mistake, I should have 48 trains going through all the different streets. Start. Oh, I should be fine with this. And I should actually increase it. Otherwise, there is no fun into that. I need to define the local. Oh, that's too many. Big compilations. Okay, not working. Why? Oops. So your monitor. I don't see anything. What did I make? I did something wrong. First, I need to do something in the LEDs for sure. Mem set LEDs. Mem LEDs. Oh. Okay, it's better if I do this. Indeed. It cannot be at two places at the same time. Okay. Not exactly what I want. Oh gosh, no. I need to. Here, what I did wrong is actually I need to get all the features before I can display it. So that's what it was doing. The compilation. Okay, there it is. So you've got the trains of different sizes. Let's reduce that so it's actually smoother, but you've got the idea. So now we have 46 different independent panel doing something, which is good, but whatever it is, I don't really make much about it. Issue is here to do that. I needed to have this huge LED buffer. Okay. Here in that case, we've got 48 times 2 is 56. It's equal to something like this, more or less something. let me calculate that with my HP28S. That's 26 times. Yes, it's 2 here. Okay. So that's the number of LEDs. And if you multiply that by 3 times, it's actually 36.64 bytes to store all that information, okay, which is kind of a lot. Okay, so first things first, what I'm going to do is I'm going to recreate that application without having to declare this or to use this as such. Okay, so I'm not going to go inside all the detail of the driver that I developed, but the driver has a nice option, which I call transposition function. When I do that here, this line, what happens is actually instead of going to a certain part of the memory to get the value of the data, it's going to call a function to calculate the value of the data. Okay, so here's actually at each, instead of looking into memory, it will call a function to get the value of the LEDs, of the pixel. Okay. So it's going to do that now. So what I need to tell him, I need to say, okay, but which functions should I call? So I need to create a functions that I'm going to call, let's say, I'm going to reduce that now. It's going to have to return this function is going to have to return a pixel. I'm going to call that function calc pixel, whatever it is. So as parameters, that it takes the LED to display, the number of the LED to display within one strip, the number of pin and the virtual pin that I'm calling. Okay, so this way I'm able to know where I am in the LED. Okay, so here, for instance, I'm just gonna, I'm gonna move that up from X from V. So here I'm gonna say, okay, if I'm trying to call that function with the number of the LEDs, so I know that which LED is going to be displayed and which LED is not going to be displayed, the pin number and the virtual pin. So the pin number is actually 8 and the virtual pin is actually what I need. Okay, so the virtual pin is going from 0 to 48, and the LED to this, I'm going to display the LED. So I'm going to recreate the train size. The train size is going to be the virtual pin plus 1. Okay. Now, if I display a LED, that means that okay, by default I'm going to return pixel of 0, 0, 0. That I don't care. Now, if the position of the LED is in between the start and the end of the train, I need to know where the train start is. So the train starts is already increased, so that's, I don't need to do that. So if I am between 0 and 2, and if I am 2, so if the LED to this, the number of the LED to display plus the trend start which I'm going to put modulo number of LEDs strip is less than the trend size. Then I need to return pixel to return 0. No, red this time. Okay, but that's not correct, I think. For instance, if I made it 0, I'm doing 0 and I'm starting at 0. So the size, start. No. Press start. And that's going to be modulo. Okay. So that should do it. Now, I'm just going to call also, but that is not needed anymore because I'm not doing it anymore. And what I'm going to do here, just to show you, I'm going to reduce that to 1. Okay. So it's only 1. Let's see. Oh, God, it's not going to work. I didn't tell him that I need to use that function. So not going to work. I need to tell my driver, by the way, here it is. I need to tell the driver, by the way, you need to use that function need to use that function. Okay. Otherwise, it doesn't know which function it needs to call to overlay. Okay. Okay. We're displaying, but it's way too much. So that's not the right stuff to do. Let's put it back to 0 here. Otherwise, I'm going to run. Okay. We're almost there, but that's not correct. I'm displaying too many LEDs and not enough power, so yeah, that's my issue. I'm going to turn everything back to black and think about it a bit more. Okay. If oh yes, it needs to be also That's stupid. To be lower and needs to be higher. Let's this need to be higher than the train start. Script and that should be better now. Not really. It's not good yet. Hmm. I don't know what that is. Why do we have to? No, that's not the correct algorithm. And why do I have? No, I don't have it anymore. I don't have enough anymore. So my code is not correct yet. I'm making a mistake. Let me see. I know it's 8 virtual pin step. Oh, I'm stupid. Okay. Going somewhere, but I think I missed that. Strange. I'm missing something that I don't see right now. I should get that pin stem 8 plus pin number. Non, c'était le pin x 8 plus virtual pin. Par contre, je ne comprends pas. I don't understand why. I should do the stuff. Oh. But I don't understand. It's not there yet. No, that's the one. That's the one. Like this. But I don't understand why. Try not to do. And I'm missing one. That's strange. I don't know if the let to display of this. Right? The trans. Okay, let's debug this because I have an issue. Okay, so let to disp pin virtual pin and also trend size. To see what where to display. I don't understand. Okay, that's normal because it takes way too long to display everything. So you. Okay, then we've got 16. So if the virtual pin is from the virtual pin can be 16, Oh yes, true, because I've made no, indeed. Okay, now it's all red. Normally the virtual times a should be this too big. No, no. Look at this. Oh, okay, that's fine. Zero, 1, 2, 3, 4, 5. Okay, and that's where I don't understand why the trend size is 0. let this in. Train size. Train size. This because it doesn't like. That seems correct. So the first one, the fifth. Okay, that's right. No, that's right. Now, let's do that. Let's do this now because it's not going to work. Remove the serial plate, otherwise it's going to happen that it will fail at the end. There's too many time spent inside the interrupt. Okay, that's good. Now it's better. So we've got the size of it. So now I can increase the train size. Sorry for the issue. I don't know what happened to my calculation. Sometimes I get crazy. And here it is. Let's see what just. Oh, yes, because I need to remove that. Did I upload yeah, I need to correct something into that to have the full train, but you get the idea. So you see that I've been able to display the train without using any memory. But if we try to do something a bit more complicated than that, inside my calculation function, what happens? So let's say that I'm putting a delay function into that. I'm going to do some strong calculation here. Let's calculate. Okay, first what I'm going to do is actually inside the, if you put your debug in verbose, your debug option in verbose, you have new information inside the I'll do this. You have a bunch of information. So let's spend a bit of time on the information that is displayed. Maybe I can increase the size of that because it seems to be quite small. size. Your monitor. Okay, so here what you have, you inside, I've made a debug inside the driver, which is actually inside of the display. So you have the number of frames that is displayed. You have the time that is spent inside the interrupt time, and what I call interrupt time, I will come back to that later. So between 20 microseconds and 22 microseconds, average time 20 microseconds. This is not important because you will see what happens if I go more than that, and etc. So now let's make something a bit more complicated inside the loop. So what I will do, instead of returning a simple pixel, I will ask to create a pixel which has a bit of fanciness into it. So let's say that I want to display colors. Okay. I want to display a nice rainbow color. So what I will do, first I need to calculate where am I on the panel. So where I am on the panel, I will remove that also. I don't need to see where am I. I'm just going to put that here. This will give me where I am on the panel X and Y position, meaning here I'm calculating where am I on one panel. Then in between the panel, I know exactly my position inside the panel. And what I'm going to do, I'm going to return a fancy function. Okay, let's see. Yes, cosinus has been calculated. Do that first, and then I'm going to you're going to see what happens. So if I do this, maybe a nice rainbow should appear. Oh gosh. Here is actually so it's 8 by 16. It's 6 times 16. Okay. Let's play that again. Oh gosh. Let's do it the first. on, not convert into pixels. No. Okay, I didn't get preview. Make that conversion automatically. Strange. Okay, it's too strong. Let's reduce that to 40. Too high of my power supply does not have support the full. Okay, ready. So here you see that I've made the graduation by finding that value each time, okay? X and Y, and it looks like this. Now look at the serial monitor. If I look at the serial monitor, here you see something strange. We see that number of pixels with unitary types more than 26 microseconds, actually 255. What happens here is actually why I do this. I make a lot of calculation and I do 48 calculations that I need to do within the 30 microseconds needed to refresh two LEDs. And because with the overhead of everything, I've calculated that if you go above 26 microseconds inside your calculation, then you're going to get in trouble. Hence, it's not looking really smooth in the display. Can we do something about it? Yes, of course we can. Because if you look lower than that, you've got a little proposed EMA extension, 130. What does it mean? First, I will show you, and then I will explain to you the impact of that parameter. So I will tell him to do what we say 113. Let's see what happens now when I put that. Oh, it's really smooth now. It's not like it used to be. Now it's really smooth. And if we look inside the serial monitor, we can see now that the maximum number of frames out of interruptions, it's only one. So I guess he's still proposing to us to still increase the number of DMI extension to 116, which seems to be correct. Okay, now it seems really, really, really smooth. And if I look by DMA, 117, 117, or we can go to 120, I think. So that means there is one pixel from 1 to time who goes above that. But now you see that the average interval is 36 microseconds with a maximum of 37 microseconds. But how does it still work? How I can still see the LED correctly, despite the fact that I'm spending too much time, more than 30 seconds in between LEDs? It's because of something really simple. If you look at the user guides of the 28-2012, you have the time to in between LEDs that you need 30 microseconds to send one data for one LED. And you've got another parameter, which is actually the time you need to wait for the LED to be refreshed next time they receive some information. And that is a couple of milliseconds. Okay? So what happens if I send two LEDs, even if it's not respecting exactly 30 microseconds in between these two LEDs, the LED will say, okay, that's still the same frame buffer. It's not a new frame buffer. And I still have a little bit of room against that. So what I did in the driver, I said, okay, instead of sending instead of giving me only 30 microseconds to send every information, I can extend that time. So I send everything 30 microseconds and I wait just a little bit before sending the next frame, etc., the next pixel, etc., etc. But my calculation can take place within, I have more time to do my calculation, but still enough, still not enough to disrupt the display. So I can extend that. Let's say if I do 400 here, so I take a lot of time to do my calculation between sending 2 pixels. And look what happens if I take too much time. Then it's totally doesn't look anything. It's not good anymore. Same code. Why? Because now I'm taking way too much time in between pixels when I send the information, and now it doesn't know what to do with the new information. It doesn't know if it needs to pass it or it's actually a new frame going on. So that's the middle ground we need to find. But playing with that parameter here, I can extend the time for the calculation. Why is it important? It's important if you have a lot of other stuff going on around your program, and your pixel, even if you're running on the second core, the calculation of the pixel at every loop, at every interrupt, can take a bit too much time for you to be able to do some other stuff within your program. You can use that parameter to give the rest of your program a bit of space to breathe in between pixels. So let's go back to 120. And it's very exceptional because here I'm calculating every time 48 pixels on the fly, which is kind of a lot. Usually you don't have more than 16 or 8. So, but you can still use that parameter to give your program a little bit of breathing space. And we are back to quite smooth transition for the LED. Okay, I can be a bit nicer if I increase. I can go again to 260 here without overriding the power supply that I have. Okay, let me play with that. Yes, with more with actually a better light, actually nicer. Okay. So now I'm going to switch screens to see how far we can go. I'm going to go to I'm switching frame. To see what we can do exactly without using memory. Okay, here I have something really interesting. You can see sprites, and they are still displayed using this calculation function, which is here. The same, I'm using exactly the same techniques. So I'm having a rainbow which turns around, and I'm having a penguin, 2 penguins, and a sheriff. It's a bit slow, right? Why is it a bit slow? Because I'm displaying at each frame, I'm displaying too many information. So I'm going to remove, I'm going to recompile it using only info information and not verbose information, because the verbose information takes too much time to display. It's interesting. I've created that so you can have a better view of what's going on inside your driver. If you're doing something a bit specific, you can know exactly how long does your program stays in the interrupt, and you can adapt your program accordingly. Okay, now it's getting faster. Why? Because we don't use anymore the verbose mode. Okay, let me stop here for a minute. Normally, I'm displaying 256 LED times 48, but one strip is 256 LED. And if you calculate the refresh rate for 256 LED, you should get 128 FPS. If you look at that, you see that I'm running at least at 60 FPS. So more or less half. Why? Because to be able to display everything that I want to display in one turn, I need to extend by 266 my DMA extension. What happens if I reduce that to 100, for instance? So now you have to imagine that at every more or less 60 microseconds, I calculate every position for all the sprites, and I put them on the screen in live, because I don't use any memory at all to do that. Okay, get ready for some messy, I would say, really messy. Okay, so it's totally blurry because you don't see anything. But what I can do is actually I can, to show you, because here I'm with 60 parallel pins, it's like 48 parallel strip. You don't use that often. So if you want to go to 16 strips, that's what we usually do. I just need to say even 3. That's 24 strips. See how low I need to get to be able to display everything without extending my DMA buffer. Here I'm only using the bottom part of my panel, and here you see that even with even with that low information, I can do it. Now I'm back into 94 FPS. Let's put us in verbose mode to see if I can reduce my DMA buffer. Okay, if I look at the verbose mode, here. Okay, I have no pixel out of time, and I see my maximum interrupt time is actually 24 microseconds. So I think that I can even, with only 24 strips, using 24 strips, I don't even need to have to use DMA extension. So if you use 16 strips, you can actually control, do something really complicated without having to extend for DMA extension, and create panel with how many strips as you wish without having to use a bit of memory. You need power under the hood, of course, otherwise it will not work. But with that, you can drive 2,000, 50,000, 100,000 LEDs with no memory at all. Just a clever calculation. Okay, if I look at that, okay, after a couple of pictures out of time, yeah, we need to estimate to make 60. And if I reduce to 16 strips, 16 panels, it's even lower. So what I spend a lot of time in is actually in the code, optimizing the calculation of everything within the driver for the transposition, and so to be able to reduce a maximum the time spent inside the interrupt. So I can do a couple of crazy stuff at the same time. Here it is. If I look at that now, yes, now I have zero pixel above 16. Okay, and it's slow because I'm displaying all the frame rate is low because I'm displaying all the information at each frame for the driver. But it's kind of nice to know what's going on. Yeah, and normally if I remove the verbose option now, back into info only. I've made a nice macro which is called how long. I love to use this macro because it gives me the time for a certain function to execute, and it gives me the FPF of the function. Still compiling the sketch. It's faster. And if we look at that, now we're back at 100 FPS, more or less, instead of the 120 that we should have because of the lack of extension here. But, I think we can go 20 here. without destroying the pictures and getting still a NIAS. Yes, 120, 118 FPS. Okay, so we're getting close to the 100 FPS for the above 100 FPS for the display, the refresh rate. Okay, let's get back to moving all across my entire panel. And it was 300. I don't remember. Something like this, I think. But that's only if you're using full calculation without if you're using transposition. Okay. So that was the technical part to display with no memory at all, a lot of information. Okay, let's go back that we have an SP32, we have a 10C, whatever, we have more memory. What can I do with that, with if I have more memory than that? Okay, so let's go back to our new program here. Up, it's in here. Let's say, okay, now I don't use that because I'm not going to use the transposition function anymore. I'm going to be old school guy displaying data. Okay. Let's okay. I'm just going to add a +1. You will know afterwards why I do that. Okay. Now, let's say that I want to display something which is actually smaller than the size of my panel. Okay, so I will do here. No, I'm going to change into something that I would like. That's my total number of it. Even if I don't use that many layers, I'm going to say that my numlet is not that anymore. Actually, times net width. Always between brackets. Do not forget that. For the moment that it's 128 by 96. If we use a calculation, 96, 198. Okay. I don't know if you remember that we can create a mapping function because I want to be able to map everything that I display. So here, what I will do is I can do that anymore. I want to display, I've got 86 lines. I want to display a line across the 86, 96. I want to have a train for each line that I have. So if I were doing it normally, I would say for int e equal 0 where let 8 plus I'm going to create a train of the size of the number of the LED. Okay, so in train size, I'm back into my train. I love that. equal I plus 1. I want to have the first one, and I'm going to go for int j equal uh, 0, j less than frame size, j plus plus, and I'm going to say the LEDs. Normally, if I'm at 8, that's I times LED width plus j plus start train LED width equal cell 255. Okay. So I've got a panel of 96 by 128, and I want for each line to display a small frame. That should be the code. If I execute this like that, oh, here, just gonna copy the same. What happens if I do that? It's not gonna look. Let's see what happens. Oh yes, that's not available. Okay, that's not what I really want to have, so that's not really good. I'm gonna reduce the search. But that's pretty normal. That's oh, I need to clear the LED too. Time. I'm not clearing the LED, so of course it's always a bit messy. It's beginning to be all right. I don't think my board will return. Oh, the right. Times 3. Okay. So you see, it's not correct. We got back into the first trend that we had. Why? Because our LEDs are not arranged on strips. They're actually panels of 16 by 6. So if you remember, we put a function that we call a map function to be able to do the mapping in between our physical LED and what we represent into, I would say, the virtual part of the LED. So let's do that again. So what I need to do to tell my driver to do so, I need to tell him, okay, now we're going to use a mapping. I have several ways of doing mapping. Yeah, I'm gonna do first. The soft mapping, and then I'm gonna do the hardware afterwards. Okay, soft mapping. Now I need to have a mapping function to tell him, okay, when I want to display, when I'm displaying one LED within the panel, actually that's referring to another LED within my array. So if I'm not going to repeat what I've done the other time. So I'm going to have my mapping function, which is for my panel. So based on the LED that I want to display, it's going to return the real position within the LED array that I want to display. So it's purely a mapping function. It's the same as when you have that basic calculation when you do snake patterns, but here is actually a bit more complicated, but it's fully adapted to my panel. And now I'm going to tell him, okay, by the way, now that you've done that, you need to use my mapping function to do your calculation. Yeah, in the setup, I would say, by the way, I've defined a map function, use that to map. I need to. So if I'm not mistaken, now we're going to see the lines going from right to left. Here you see, because I decided to have a nice triangle, because for each line I'm going 1, 2, 3, 4, 5, 6, 7, the size of the triangle being the number of the. So now it's mapped correctly. Okay, good, that's fair. But now I'm saying, okay, but I don't want to display. I don't have enough memory to display a 128 by 96 picture, because my memory is not enough for that. Let's say that I'm going to do 32 by 32. What will happen if I do that? It's going to be a mess, because it's going to try to look for LEDs, but I don't have enough LEDs, because I need 10K LED, 12K LED, but I'm only 1024 LEDs defined in my panel, in my LED array. But my panel is way bigger than my LED array. And that's not good. Okay, so let's go back to 128 by 96. Because it's going to look for information inside the memory, but it doesn't find it, of course, because it doesn't know where to find it. How can we solve that? So what we're going to do, we're going to tell him to do what I call a hardware scroll map. Okay, here it is. Now it's good. And we have a new object within the driver, which is an offset display. So we're going to tell him, by the way, this is the size of my display, and this is the size of what I want to display inside of it. Okay. Okay. So I'm going to define a new object, which is offset display. And this object has a lot of properties. And I'm going to tell him, okay, here in my setup, I'm going to say, okay, my display is defined as such. My real panel to display is actually 128 by 96. Real size of my display. What I want to display is actually that now. Image this. Okay, that's what I need to display. And instead of asking him, and I'm going to tell him, by the way, now I'm going to display my information, but using that parameters for my display. So I'm going back to 38. Normally, if I do 128 first, because actually, yes, I did that correctly. So normally, if I do that like this, it should not change anything. Because I'm just displaying. I said that the size of my array is actually let with let 8. Maybe 16 by 16? No. Oh, yeah, I forgot to put the try. Okay. I forgot to get the default driver of that. It's not needed anymore. Okay, there it is. Now it's back. Now I'm going to tell him, okay, now I want 32 by 32 because I don't have enough memory. I can only display 32 by 32 pictures. So you can imagine that you can have a display which is, I would say, 2000 pixels by 2000 pixels. And you don't have the memory for that, but you want to display something which is smaller inside that array. And here it is. So here I have 32 by 32. I still have the same animation in 32 by 32 within my big display. Yes, but if that's really nice, but then I'm losing a lot of real estate here because I can't do anything. First things first, I'm going to move what I'm displaying. So I'm going to say, my offset is going to be, I'm just going to put it in the middle, for instance. Minus let width. Yes, no, it's 28 here. That's 8, so it's 128 and divide by 2. minus let by 2. Okay, so now I've moved the display in the middle of my huge screen, which can be whatever size I would like. Okay, but I'm still losing a lot of real estate. So what I'm going to do first, so that actually it's more, we get better. So there is my animation. And what I'm going to do, I'm going to create a frame around my animation in white, for instance. So first, I'm going to tell him let width. No? I'm going to tell him to draw one line. So no, we're just going to we're going to say let's. The first row is going to be I equal so it's white. The upper part is going to be also the same, so that's plus let 8 minus 1 times let width. Yes. And then here, I'm going to say that I'm going to add let of okay, at the first pixel of the line and the last pixel of the line should do that. So if I'm not stupid, I'm not that stupid, normally we should have a white frame around my small animation. Yes, you. Wow, it's blurry coming from the LED, but coming because I guess the white is maybe too big, so my camera doesn't. It's too bright for the camera, so let's do that. I could have defined one color. Okay, looks nice, but I guess yes, my camera seems to be okay. So now what I'm gonna tell him, okay, now we have real estate, so let's duplicate what we have. So we're gonna say enable loop x equal true. What will happen in that case? It's going to duplicate the image within the size of my big panel. So let's say I have here, it's actually 32 by 32 within a 178 by 96, but I could have like a 10,000 pixel by 10,000 pixels, but only displaying a 100 by 100 by 100 pixel pictures, but it's going to duplicate automatically that. And I'm still using only as size of my array, only that. Okay. Now I have a +1 here. Why did I put a +1? If I do this, let's of numlets. Maybe we never have to do that because it will go outside. Let's put it at pixel 20, 20. It gets a background color. So I put it like here. I could have defined a background color as an object. Actually, I could have done that. But by doing this quite easily, if you define the last color outside of just the one outside of your size array, it becomes a background color. Okay, the same way I have enabled the duplication on the X, I can enable the duplication on this. So now I'm full with every time the same animation repeating. I can change the size of my animation. Let's make it rectangle instead of square. And here it is again. Okay. But I can go even further than that. Let's put something which is odd as a number. Because now it seems that the animation is actually moving from one screen, from one small array to the other. It's something a bit really should not. Oh yes, it's still continuing. Yeah, okay, whatever. Okay. But now I can say, okay, but it's nice. Okay, let's remove that. Let's remove the enable X and enable Y. So it's just going to be one rectangle in the middle. But I want to say, okay, that's good, but I would like the same picture to take more space without having to do anything. Like I would like to scale it. Okay, let's move that. Hello. Because yes, it's too shallow for the color. Let's remove. Okay, so now that I moved it by 2, I need to change the center of it. To move it back. It's killing everything up and down. So now I have scaled the image that I'm displaying. Okay, if I can put that to 0, you will see exactly what I mean. Same image, twice bigger. I can make it twice smaller. And of course, because that's totally random, you can do that. So it's actually variable, so I can do this. Getting x equal, let's say something between 0 and I. So let's say cos of we're going to do a +1 anyway. Cos of train start divided by times pi 3.50 divided by 100 +1. Okay. Normally, you should have the size going bigger and smaller, bigger and smaller at each. But of course, I can back into the combination of it also works like this. So you see that you can do almost whatever you want. It works with smaller or bigger picture, of course. Yeah, that's not only on small on huge and small on a smaller picture, but it can be used also for bigger pictures. So you can move the picture, display them more or less at the speed that you'd like to, which is actually kind of nice. So you can display whatever you want, wherever you want. however you want. And we have one more to display to show, which is actually we can spin it around too. Okay, so let's put everything here, that. And now I'm going to say, by the way, rotate the image. Yeah. It doesn't find its rotation. Why doesn't it display the no? Let me check because I don't remember the single for the display rotation or yeah, rotation on rotation equals, let's say that. Yeah, let's remove the scaling for now. Anyway, yeah. So the animation is within the square, and I'm rotating everything all together. Okay. So as I said, with theta, you don't need, you can control 100,000 LEDs, even if you have the memory of maybe a couple of thousand LEDs. You just create the animation for this couple of thousand LEDs, and then you duplicate everything. And now let's add the scaling into that. Anyway, scaling, rotation, and I would like to be even further. I could also have movements around, which I could do like this actually. Okay. What I'm gonna do is actually move the rotation point plus cos. Let's move it by 10 times cos of that. Divided by 2. Yeah, same thing, but I'm gonna do a sinus. And if I want the rotation to be still correct. I need to add the same transposition for where rotation is. Okay, and normally it should add also, the screen should also move like this, like in a circular pattern. But by 10 pixels, maybe it's not enough to see something. The rotation maybe could be too fast compared to the. Yes, what I'm going to do is I'm going to differentiate the speed of that. And I'm going to put like 50, 50. So it's going to not be in the same phase, and with more amplitude. Yes. And now you see that it's also, panel is also moving along. So I can even do that. 10, 10, 10, 10. I want more motion, lateral motion. Yeah. There it is. Everything combined all together. Okay. And inside of that, we do everything. But what happens if I put here, I put something which is smaller? Let's put something which is back. Normal size of my panel. What will happen then? Are we going to crack something? Destroy something else? No, it's just going to scale down and scale up until its maximum. So now it's 2 times, but 2 times bigger, but 2 times it's way larger. Okay. And if I decide to pay something that is larger than my display, so 200 by maybe 150. Actually, now my LED array is wider than my physical display. What will happen then? Normally, yes, I have enough memory for that. Yes. Still reducing it and still displaying even if it's wide. So now if you can, now you can imagine that you can have a huge feature to scroll. You defined using that offset display parameter, you define the size of your image and the size of your physical panel. And then you can move it around, scroll it in all 4 directions, resize it, scale it, rotate it, everything within the driver without having to add any code at all. Which is, I think, it's kind of nice. So it reminds me of, for those who know the Game Boy and the NES, of hardware rotation and of sprite and background, etc. 78 by 9. There's going to be a small rectangle of this height of the Yes. Let me see if someone writes me. Okay. So this is for doing a lot of crazy stuff within with the driver, internal driver. And that you can play that around 16, 20, 120 scripts if you want to. But using that, you do all the transformation within the driver and you respect the mapping that you have. Otherwise, you don't do anything. Now, what I'm going to do, but it's a bit early, something that doesn't exist yet in the driver is actually taking into account sprites directly inside the driver. Because here I can do rotation of objects, but I cannot add individual sprites which are independent from the driver, from the LED array. So I propose that next time we do that. And if you want to, for those who know the PPU, I think it's going to be a nice series to reproduce, to create a LED driver, which is actually a PPU, like for the Game Boy. So normally, if we do that correctly, we should be able to have a PPU as a driver for driving LEDs. I think it can be funny to display a Game Boy image using that. Let me know if you would like to tease that. Okay, I guess it's going to be all for today. It's going to be a short one. I hope you liked the stream also. Sorry for the slow beginning. I don't know what happened with the music. Caster did not work at all today, which is not that good. But I hope you will like the rest of it. So please do subscribe and come back for the next one. Bye bye.